cloud computing. The Google file system today we will talk about. It is called GFS, Google File System, GFS. It is a scalable distributed file system for large distributed data intensive applications. Multiple GFS clusters are currently deployed. The largest ones have 1000 plus storage nodes, 300 plus terabytes of disk storage, heavily accessed by hundreds of clients on distinct machines. Introduction, let us have shares many same goals as previous distributed file systems like performance, scalability, reliability, etc. GFS design has been driven by core 4 key observations of Google application workloads and technology environments. Observation 1. Component failures are the norm. Number 2. Huge files by traditional standards. Number 3. Most files are mutated by appending data. Number 4. Co-designing the applications and APIs benefits overall system by increasing the flexibility. The design. Cluster consists of a single master and multiple chunk servers and is accessed by multiple clients. The operation log will be as follows. Record all critical metadata changes stored on master and replicated on other machines. Defines order of concurrent operations. Changes not visible to clients until they propagate to all chunk replicas. Also used to recover the file system state. The system interactions, releases and the mutation order will be as follows. From the client, it is going to the secondary replica, then it is going to the primary replica, and then it is going to the secondary replica. So in between, the other routes are there. Say for example, from client you can go to the master, from master you can go to the client. From client you can go to the primary replica, and from primary replica to client you can go. Similarly, secondary replica to primary replica you can go, and vice versa. Secondary replica B to primary replica you can go, and vice versa. So this is called the system interactions. Next we will talk about the very important concept, namely the map reduce. Consider the problem of counting the number of occurrences on each word in a large collection of documents. How would you do it in parallel? Map operation. Map, a pure function written by the user, takes an input key or value pair and produces a set of intermediate key or value pairs. Draw an analogy to SQL. Map can be visualized as group by a class of an aggregate query. Reduce operation. On completion of map phase, all the intermediate values for a given output key are combined together into a list and given to a reducer. Can be visualized as aggregate function, example as average, that is computed over all the rows within the same group by attribute. The map reduce execution. The map reduce execution will be from the user program, it is going to the workers, and from the user program it is going to the workers in all direction. From the user program you can go to the master, and from the master you can go to the worker, like that. So all these possibilities are there, and you can see a normal diagram in any standard books about this. Map. Next is the page ranking concept. It is very important. It's a page ranking concept, and map reduce and some more applications. So distributed grip, count of URL access frequently, and clustering k-means, and graph algorithms, indexing systems. And other extensions and similar applications are PIG, that is Yahoo, Hadoop, that is Apache we call it, and then Dry Lake, that is from Microsoft. Large scale systems architecture using MapReduce. From the user application, it is on the top, and then MapReduce, and then distributed file system, GFS namely. So this is the architecture with respect to large scale systems. And you will also have a concept called a distributed storage system for structured data, and a big table is a distributed storage system for managing structured data. Designed to scale to a very large size and used for many Google projects. It is very flexible, high performance solution for all the Google's products. Motivation. A lot of structured data at Google, URLs, contents, per user data, and geographic different locations, and scale is large, billions of URLs and hundreds of millions of users, and 100 terabytes plus satellite image data. So why not just use commercial database? Scale is too large for most commercial databases. Even if it were not, cost would be very high, and building intensively means system can be applied across many projects for low incremental cost. Low level storage optimizations will help the performance significantly. Much harder to do when running on top of a database layer. The big table. It is distributed multi-level map, fault tolerant, persistent, scalable. Scalable in the sense thousands of servers, terabytes in memory data, and petabyte of disk-based data, millions of reads and writes per second, efficient scans, self-managing. Servers can be added, removed dynamically. Servers adjust to load imbalance. The big data model. A big data is a sparse, distributed, persistent, multidimensional, sorted map. Web table examples. Want to keep copy of a large collection of web pages and related information. Use URLs as row keys and various aspects of web pages as column names, and store contents of web pages in the column until the timestamps when they were fetched. Rows. Name is an arbitrary string. Access to data in a row is atomic. Row creation is implicit upon storing data. Rows ordered lexicographically. Rows close together lexicographically, usually on one or a small number of machines. Again, rates of short row ranges are efficient and typically require communication. The small number of machines can exploit this property by selecting row keys so that they get good locally for local access. Thus, I have given you some ideas on Google file system concepts. Hope you might have enjoyed.